All right, welcome. In this video, we're going to take a look at the hash table data structure, which is a very commonplace data structure that you've probably had a chance to use before. And we're just going to look at sort of the standard implementation of a hash table and then some of its variants. So to get us started, I want to remind us that the hash table is a common implementation of the map. Now, a map is an abstract data type, meaning that that sort of lives in the realm of the abstract, but we implement it, we create concrete versions of it in different programming languages, and usually we usually call them a map, or there are a couple other names for them as well, associative array, dictionary, and so on. But we're going to talk about them and call them maps. And so this type of abstract data type, what really characterizes it is that it relates two pieces of data, a key and a value. And we sort of looked at this in a previous video when we were talking about B-trees, that often if this is being used, say, in a database setting, the key is something simple and small. More often than not, it's just an integer, which is, we're going to see in a second, is convenient. And if it's not an integer, then it might be like a string or something simple like that. Usually nothing too much more complicated than that. But whereas the value can be of, again, arbitrary type, but is more likely to be quite large. And that's because it is more likely to be a record that stores all kinds of pieces of data in it, aggregate pieces of data, as well as maybe whole lists of other pieces of data inside. So think of a student record, might have a list of your classes with your grades, or a bank record might have a list of transactions, or social media, your social media account might have a list of your posts, and so on. So all of those cases, those would be large records that would fit in for the value stored in the map. The key then would be your ID number, your student ID number, or your login ID that allows you to find that particular record. Now, we're going to consider here a couple possible implementations, keeping in mind that when we have an abstract data type, that gives us different options on how we might want to concretize this data structure. And so the simplest way to do it, and this we might call this the naive way, is to just pick the simplest data structure available to us, which might be an unordered list, and see if we can make it work. Now, a map is characterized usually by two specific methods, get and put. But I have listed here a couple other operations we might want to do on the list. So get and put, of course, are going to be our simple lookups. They have hidden in there sort of a search. Contains key is the technical search one. Contains key is just going to tell you yes or no if the map has that key. But get and put usually sort of implement the search as a first step. Get being find that key, the location of that key, and then tell me what's stored there, if there is anything. And then put would be find the location of that key and then overwrite it with some new data. Delete, again, also sort of implements that search, find that key, and then remove the data. And then contains value is the only one here that sort of doesn't use that search for the key, because it involves searching for the value instead. Instead of searching over the key parameter, we search over the value. Now, if we have here our map implemented as an unordered list, then the search for the key means searching the whole list. We don't know where it is. We've just stuck these keys, or key value pairs rather, into the list with no order. So we have no advantageous way to find our key other than just iterating over the whole list. So that's order n in the worst case. Since there's nothing special about searching for keys versus searching for values, the same thing is true for searching for values. And again, remember that these three, get, put, and delete, depend on contains key. So we can see that in all all of these operations, it's going to take us about order n to carry them out. The only other operation that I'm going to consider is sorting our list, and here I'm considering it sorting by key. So I said sorting my list, that's the implementation, but let's say we want to sort the map, and we want to sort it by the key. We could potentially want to sort it by the value. I'm not going to comment on that one as much, because none of the data structures we're going to consider are going to keep our map in order of the value. If there were, then in those situations sorting by value would be easier. But so what that means is in any case where we want to get out our map in order of value, we have to perform a sort, which is where we're getting this n log n runtime here, assuming we're using an efficient sort here, meaning we have a large enough n that we want to use a merge sort, or a heap sort, or a quick sort, any of the sort algorithms that have an n log n running time. If our list happens to be small enough, our map happens to be small enough, we might just use a bubble sort or an insertion sort or a selection sort, whichever n squared algorithm we might be happy with. I have a little comment here that if we're going to use this implementation, it's best if we have small maps underlying this. Now, what is small? I'm just going to throw out a number of 100. So in a lot of the homework that you may have done through your programming classes, you may mostly encounter maps of size 100, 200, 1,000, something like that. These are fairly small. If you had to implement these yourself, if you weren't relying on built-in maps, say, from the programming language you're working with, then you'd probably be okay to just use an unordered list, throw the elements in there, and do simple sequential searching to find the ones you're looking for. And if you need them sorted, just run the sort procedure. Now, that's the idea here. Well, what happens if your n gets larger? What if your n is large enough that that starts becoming prohibitive? You don't want to be doing order n just to find elements. Well, that's where some of the data structures we've already looked at come into play. The primary data structure that we can use in role of a map would be a binary search tree. Now, a binary search tree, so far as we've considered it, stores the key. We've sort of just ignored the fact that there's usually a record attached to that key along the way. But the binary search tree allows us to organize those keys in such a way that we can search for them efficiently. Okay, and now, not just any old binary search tree, but as I've sort of indicated here, a self-balancing binary search tree, or as we looked at in our previous videos, the B tree would be another alternative here. In all of these cases, as long as we have self-balancing or the B tree, we're guaranteed that the depth of our tree is logarithmic in n, and so what that means is that we have our search operation, our contains key, and then these three operations that depend on it also having logarithmic runtime, depending on the depth of the tree. Okay, now again, the base of the log might be different depending on which tree we're trying to implement here, but also keeping in mind the change of base only spits out a different constant out front here. So all the trees will be log n in their implementation. So again, the contains key, which is the searching for keys, is the more efficient operation because, well, that's what a binary search tree is designed to do, allow us to search more efficiently. Because these three operations all depend on contains key, they'll also be log n. However, contains value, we still need to search the whole tree, meaning we need to do a full traversal of the tree, which is going to end up being order n. Again, the binary search tree will keep our keys in order, but it does nothing for our values. Okay. Now, if we want to sort by our key, because the binary search tree and the B tree will keep our keys in order in the sense that if we do an in-order traversal of the tree, we get them out. Well, the in-order traversal is also only one traversal and only order n. So right here is the primary benefit of using a binary search tree or B tree implementation of a map, is that if you need your elements out in order of the key, you get that for free, basically, if you keep them in a binary search tree. Why do I say that's for free? Order n doesn't usually seem for free. Well, the minimum amount of time it's going to take you to output your elements in any order is the amount of time it takes to just write them out or read them or whatever process you're using that for. So here, the actual steps of sorting here is actually zero effort, because all we're doing is reading them out in the order that they are currently in. So that's sort of zero effort or for free. However, the whole process of reading them out will still take order n, but that's sort of the cheapest we can get it. So we've sorted our list by just keeping them in this data structure. Now, my comment here is we're probably going to want to use our binary search tree implementation, or B tree, if we have sort of middle-sized maps, larger than these small maps that I was considering before. And larger here, maybe if we were saying hundreds or thousands here, maybe hundreds of thousands or millions for mid-sized range maps. Or, and this is sort of an important emphasis, or large maps, which means any size. When I say large maps here, is just anything else. But that we want to keep them in order, and that's because, remember, we get this part for free. So that's, again, the main benefit, and so we may use these binary search trees instead of a hash if we need them kept in order of keys. If there's a regular operation where we need to output them in the order of key, then we might keep them stored in a B tree or other self-balancing binary search tree. Okay, which brings us to the topic of this video, which is hash tables. So hash tables, as we're going to see, have the implementation such that our contains key, our search, and then of course the other three operations that depend on it, get, put, and delete, all occur with constant time. And the way we can do that, as we're going to see in a second, is we're going to rely on random access memory, which we get from an array. And so instead of sort of keeping it unordered, we're going to remember through our hash table where each element is, and that's going to allow us to, instead of having to search for our elements in the array, just go grab the element out by knowing its address or its index, technically. Okay. Now there's a little asterisk here with reasonable assumptions, but that's sort of an important, there's sort of two pieces here. One, there's some assumptions. That's important. The asterisk is saying, hey, there's something else behind the scenes going on. And then me saying they're reasonable assumptions is me trying to sweep those things under the carpet by saying, okay, well, there are extra assumptions going on, but I think they're reasonable assumptions. So most of the time we should say, okay, we think that this is true. And that is a good way to walk away. If you're done with the video right now, you need to walk away, you should assume that hash tables have order 1 access for these operations. However, later on in the video, we're going to talk a little bit about what those assumptions are to fill in some of the gaps. And then maybe you can use your own judgment to decide if you think they are reasonable or not. Or maybe another way of saying it is you can build up your judgment so that in the real world, if someone comes at you with these assumptions, you can use your own judgment to see if they're reasonable or not. Okay. Also in our hash table, our contains value is still just going to be a search. So we've seen that here, and we've seen that here. Our contains value hasn't really changed. We still need to search all the elements for that value. However, our contains key is the one that we've optimized. Sort by key, well, this is again the trade-off between these two models. If this was not the trade-off here, if we could sort by key in order n here, then there would almost be no reason for us to use a binary search tree or B tree implementation. So what we find is that we're going to probably use the hash table for the majority of our map implementations, except when we have this extra requirement here that we need them kept in order. And this needs to sort of be a strong requirement. There needs to be some sort of strong requirement for us to do this. Now, with that said, in modern databases, We don't worry about this trade-off because the extra memory it takes to store the hash table or the B tree is nothing to be worried about. And so instead, what we usually do is we have as an index on our a very large database, we probably have a hash table index and a tree-based index, which means we can use the hash table index if we need to just find elements in random order, meaning random access order, but then we can rely on the B tree index if we need to sort them. And again, maybe the process where we're using isn't a full sort. We don't need to full sort them, but we maybe want to iterate through a few. Maybe we want to look through a section of the list in order of key, and that's easiest to be done if we have the B tree. And if you want to learn more about that, I would definitely say take a look at database implementation, where there's sort of lots of clever ways to sort of blend multiple data structures, actually, including a linked list as well, to have all of your elements stored in very easily accessible ways for different types of accesses. Okay, so this is just a heads up on sort of different implementations of maps, and then today's goal is to take a look at a hash table and justify some of these values we've got here. All right, so how does a hash table work? Well, a hash table itself is going to be a table. Okay, that's sort of the first piece. And then we're going to use something called a hash function. That's, I guess, the other piece, to locate our keys in the table. So for the moment, every once in a while I'm going to bring up values, but for the moment I'm going to just kind of assume we're once again ignoring these values. Push them to the side, focus only on the keys. The keys, remember, are unique, so we only have one key or one value attached to each key, but it's the keys that we're trying to organize for efficient retrieval. Okay, so we're going to assume that we're going to store these keys in this table, and we're going to use this hash function then to find keys in the table. So how does that work? Well, our table is just going to be a simple array. So just think of, the simplest array in whatever language you're comfortable in. And then we're going to have this hash function, which we can think of in two ways, both as a mathematical function, but also as a computational function. So mathematical function in the sense that we're going to use it to compute some mathematical function, but in the second hand, we probably need to implement this mathematical function in some way in our code when we want to implement our hash table. Now, what does this function need to do? It needs to map. Here I have the word convert, but this is where we get the name map for our data type, is that it's supposed to map from the key to an index into our array. So it's going to take that key, whatever it is, and turn it into an index in an array. Another way of thinking of that is for every key that we might have, we're going to assign it an address in our array where it belongs, and we're going to rely on that so that when we're looking for our key later on, whatever operation we need to do to look for our key, we just ask the hash function where it belongs. Which index does it belong in? So here I've made a hash table, an example hash table. In this hash table, for simplicity, I'm going to make our keys to be integers, and that's usually assumed when we're talking about hash tables. We usually assume, well, for the most part, when we're talking about any kind of map, we usually simplify things down and assume our keys are integers. But if they're not integers, we'll see in a second how we might want to deal with it. There are a few clever ways to deal with that. But for now, let's assume they're integers. And actually, I'm going to assume my integers are in this range from 0 to 255. Okay. So I've got keys in this range, but then this is the hash table that I've created. And for the moment, look only at the light blue here. These are the indices into my hash table. So my table, as I said, is a simple array. So it's really just this blue bit. But I've written the indices here to make it easy, obviously, for us to also see what's going on here. And then to place elements into the table, I've used the mod operation. So my key here is going to be a number between 0 and 255, but the indexes into my array, as I see here, are going to be values between 0 and 22. So we need some method to convert the keys into indices. Now, as you can see here, the mod operation does that job for us. The mod operation here will give us a number in the range 0 up to the value that we're doing mod on. So since we need a value between 0 and 22, we're going to do mod 23. That's how many spots there are here. And that every value in this range will be mapped to one value in this range. Okay, and we could probably go through here and do a quick verification for all these numbers that I've stored in here. I've done mod 23 on them to find where they belong. A couple of them I think are going to be easy. We can see 3 is stored in 3 because 3 mod 23 is 3. 11 is another easy one. 11, right? 11 mod 23 is 11. Okay. 18 fits that pattern too. So those were a couple easy ones. But let's maybe check this one. 27 mod 23 is going to be 4. 23 plus 4 is 27, right? 23, 24, 25, 26, 27 belongs in this location. Okay. Again, 30 it looks like is, if that's 27, it belongs here. 28, 29, 30 it looks like this one also is in the right location. Again, we can verify this. If you need to, go through, punch in your calculator for each one, mod 23, and make sure that each one is in the right location. Okay. Now again, what that maybe means for us, if we want to perform an operation like find one of these elements, let's say we want to find 40, what we would do is we put it through our hash function, k mod 40, or sorry, 40 mod 23 is 17, and 17 is where we find the value that we're looking for. I said node. Why did I say node? Well, because this is a key value pair. It's a key, that's what we're looking for, but hidden behind that key we're sort of hiding is a link to the value, which is probably a big record. So maybe this is student ID number 40. What's behind there? A big record. Okay. Okay, so again, what the takeaway from that is that finding where any element belongs in the hash table is as simple, at least in this case, as performing the mod operation. And performing the mod operation gives us the index, and then we're done. And some of you might already be thinking of a problem with this setup, which is good. You're ahead of the game then, but we'll tackle that one in a second after looking a little bit closer at this. So again, if you need to, go through and verify these values are in the right place. If any of them are not, let me know. Okay, and I'll try and go back and fix those. Okay, so again, I think maybe I've highlighted a few of these things, but let's just review them again. So the hash table is the simple array. We looked at that. Positions in the array are called buckets. That's just a convention, and I don't think I said that yet. And as we sort of saw in our example, they may or may not store an entry. Okay, so here we've sort of got a convention with the linguistics, the different language that we use. I mentioned bucket is what we call where we place things. Well, entries are the things that we say we put in there. Now that I say entry as opposed to key because an entry is assumed to be a key value pair, or as I mentioned just previously, we might call it something else like a node. So think of buckets as sort of being empty but can be filled up with things. So buckets are locations in the array, whereas entries are the things we're going to place into buckets. Okay, so that's, I guess, the next thing I say here. Entry is a key value pair. Okay, the key, its role is to identify the element, so identify our entry here, and we store it along with the value. So usually we think, we might think, hey, It's the value that I'm actually trying to store, the record, right? The key is just telling me where to store it. So maybe I don't need to store the key there as well. That's sort of a waste of space. Well, two answers. One, in the modern era, it's definitely not a waste of space. We have plenty of space to go around. But also, we usually need it to identify which key it belongs to. So once we see the value there, we want to know which value does this belong to in case of an error, as we'll see in a second. There's the potential for some errors. Okay. The value is the record, but as I've mentioned a couple times, we don't usually store the value actually in the table itself, just as we wouldn't store it in the B tree or in the binary search tree. We would store a reference to the value instead, mostly because the value is usually large, and because it's not just usually large, but it's often of an unpredictable size. So we don't even know how big a chunk of memory to keep available in the node, for instance, for the value, unless, as I have sort of pointed out here, it's very small, meaning maybe the value is just an integer. If it's just an integer, then fine, we don't need to have an extra layer of reference there. But more often than not, we're going to have our value stored just as a reference. So again, in my examples here, I'm probably just going to ignore the value most of the time. And then I think I highlighted this, but let's just mention it one more time, that the benefit of storing our elements in our table in this way is that we're going to rely on random access, which means if we know the index where our element is, we can access it with order 1 time, okay, constant time to fetch it, which is how we're going to achieve our order 1 access time for the hash table. Okay, so one thing that, another sort of piece of jargon that we should sort of highlight, there's a slight difference here. We might talk about the size of the hash table, or the size of, or the capacity of the hash table, and these are going to be two different things. The capacity is actually the size of the underlying array, and then the size is going to be how many entries are actually stored in that array. Okay, and then often we can talk about sort of the ratio between these two. Usually there's going to be empty space in our hash table, so that our capacity is larger than our size, and so this ratio is usually less than 1 if we compute size over capacity. However, every once in a while, if we have a little bit extra storage built into our buckets, we could have a size that's greater than our capacity. We can overfill our hash table, and we'll talk about that in a sec. Also, for now, we're going to consider cases where our arrays will grow in size, meaning we might add entries, but we're going to stick with a fixed size capacity, a fixed size array. And this kind of hashing is called static hashing. And what that means is if we fill up the array and we decide we need more space, then we're going to do what's called a rehash. And a rehash is a very expensive operation where you basically dump everything out of your hash table into a different hash table. And we do have to perform that operation now and again on our hash tables. Again, think of a large database, not just something that's in memory for a short period of time and then deleted. But for a very large database where we have a large hash table, where maybe it's grown and grown and grown and we need a bigger one now, we'll do this rehash. That might take a long time, and if we don't want to disturb database access while we're doing that, then often what we will do is we'll perform that during one of these database maintenance cycles. And so you may have encountered this if you've had access to a database before. This is a little bit sort of older school, where you might have a period of time during the night, usually like 3 in the morning. It says database access will be shut down for however long for maintenance. Well, it might be because we're running an operation that is rehashing the whole database, and that, depending on how large your database is and how fast your machine is, that could take, a couple minutes, maybe an hour. So that's sort of why you'll see those database maintenance shutdowns every once in a while. That's something that you might not see as often anymore, and that's because sort of in a modern scenario, especially in the modern scenario where you have a website and you want the web access to be, 24/7, 365, then you don't want to have any outages for any reason. Well, if you still need to do maintenance, what you would do is you'd sort of clone. Well, you usually have multiple clones of your database anyways, so you just sort of take them down one at a time. You have, partial shutdown on one server or one clone of the database. In the simplest case, you have two versions of the database. You shut down one, do maintenance on it, while the other one is servicing any requests, and then after you're done, you reopen the new one and update the second one. So that's, again, during that type of scenario, that type of maintenance schedule, you would maybe rehash your hash table. Okay. The last little piece here I'll say is maybe we want our hash table to grow as we add elements. We don't want this static hashing business. Well, there are dynamic hashing techniques, and we'll take a look at those in a couple future videos. Okay, so one of the sort of pieces of mystery or magic in hash tables is the hash function. And this is because the goal of the hash function, or the purpose of the hash function, is to take your key, whatever it might be, and map it into one of our indexes, into our array. Now, very often, this is carried out in two steps. The first step is focused on the arbitrary nature of the key. So first of all, the key, we don't know what type it is that it's coming in. It could be an arbitrary type. In the wishful thinking case, I guess, it's an integer. But if it's not an integer, it could be anything else. It could be an arbitrary object of something. So we need to convert that into an integer in some way. Okay, if it's already an integer, as we sort of say is here, we get to skip step one. But step one is somehow taking whatever we've got and turning it into an integer. Now, when I say here turning it into an integer, I'm thinking a little bit more of the computer science programmer integer than I am the math integer. Okay, when I mean integer here, I mean some value in a range between 0 and 2 to the 32, or minus 231 and so on. Some range, some value, maybe a 32-bit integer, maybe a 64-bit integer, whatever it is, it's got some sort of fixed range on it, but that range is usually pretty large. Okay, that's sort of all that's important. So if you want to think of a mathematical integer, that might be fine too. Okay, then step two is usually, maybe with some other effort, but usually using the mod operator to just produce an integer in the range we want. Okay, so remember, we want an integer in the range 0 up to the capacity minus 1 of our array. So we're going to use mod to kick out an appropriate index into that array. All right, so how do we convert step one is the part I want to focus on, since step two is sort of the easy case with the mod operator. Well, I am going to talk a little bit just about Java, since I expect a number of you have some experience with Java. Java has built into it a hash code method. So for those of you who are not familiar with this, in Java, there's a sort of an object hierarchy, and in the object hierarchy, the top level object is called object. So actually every object is an instance of object. If you go take a look at object on the documentation, you're going to see that there's not too much built into object. One method that you've probably used before that's built into object is the toString method, which means everything can be output as a string. But another couple methods that are attached to object are the hashcode method and the equals method. And these actually do have implementations already built in for any object. So there's an interesting case here, which is that what we're saying in hashcode, what hashcode is doing for us is performing step one. Okay, it's converting the object into an integer. Now, how is it doing it? Well, the clever little bit here is it just returns the memory address of that instance of the object, unless overridden, of course. So what does that mean? What the built-in way that Java is going to find an integer for your object, your whatever it might be, is going to just look at the memory address that it is stored in and use that as the integer. Now the reason we're going to use that, again, remember I said this integer might be in range. Well, that in a 32-bit addressing system, that will be an integer that is at most 32 bits, or we can treat it as a 32-bit integer. And again, putting it through a mod operator might be a good way to find our index then. The other thing that's important about that is it guarantees that this index is unique for that object that we're considering. Because that object, only that object can occupy that location in memory. So if you take two different objects and ask for their hash codes, they'll be located in different locations in memory, so they'll have two different hash codes. Okay. Turns out this is the default built-in way for toString to work too, is if you don't override toString, you're going to get a toString that just outputs the memory address of your object. The other method that you're going to see here that is overridden or can be overridden is the equals method, where well, this one takes an other object. You have to pass in another object, and it's going to tell you if they're equal or not. Well, again, the clever way that Java does this without overriding it and telling it how to do this otherwise, it's just going to compare the memory addresses. If you've given me the two objects that are stored in the same location in memory, then they must be the same object. Otherwise, they're different objects, even if they have all the same data on the inside. And this is why, if what you want to do in your objects, you need to override this so that you can do a deep check. This is a shallow check. Okay, it only checks the memory address. It doesn't check what's written inside them. Okay, if you need to do a deep check, you need to override this. Now, because we're now sort of fully aware of what these methods do, we now see a rule that good Java programmers use, that if you override one of these methods, hashcode or equals, you should override the other one so that it continues to work as expected. And what I mean by that is equal objects should have equal hash codes. This is the expectation that we have on the performance of hash codes. If we have two strings that spell the same thing, they should belong in the same bucket in our hash table. Okay. So again, this is a good rule. If you're a Java programmer, if you override one of these, you want to override the other one. Okay. So please do that. Please go ahead and do that if you're working in Java. And let's take a look at it. One example of that is for the string data type. In Java, this is true, that in Java, that if we use the memory address technique, we're not going to have the normal performance or the expected performance for our strings. So here I have sort of two expectations. If our two strings have the same value, we expect them to be equals in our expression. So importantly, say if we have a string variable with value hello world, and we want to test, is this equals to a string literal hello world? It should say true. This is equal. We want them to do a deep check. Check the string for its contents, not to see where its memory location is. That would return false, and we don't want that. We want it to do a deep check. And then the same thing is going to be true of our expectation of the hash code. We want two strings with the same value to have the same hash code, go to the same bucket. So Java has actually gone ahead and overridden both of the methods for us. So you'll notice if you do use the string hash code and the string equals in Java, it's already overridden the built-in object versions of these methods. Specifically, the equals method works as you expect. it checks, does a deep copy, or not a deep copy, rather a deep check of our two strings. And then the hash code method actually uses an interesting technique. Now, this technique is sort of a conglomerate technique that's been built up over time using a couple different techniques sort of built into one. The first technique is just to hash character values. So hashing character values is fairly straightforward because character values are already stored in a table. Okay, so let's think about this for a second, and this is actually sort of insightful. If you think about hashing characters, and for the moment let's just think about ASCII. If you have, maybe you're counting the number of characters, or sorry, the frequency of characters in a file. If you want to count the frequency of characters in a file, you're going to want one location for each character to store its count. Well, each character already has an integer associated with it, a unique integer associated with it, which is its ASCII character value, and we know that's an 8-bit string. So we can take that 8-bit string, treat it as an integer, and then use that if we need to with a mod to put those characters into some hash table. So hashing characters is straightforward because characters are already associated with integers. So let's piggyback on that and see how we can hash a string now. Now a string, let's remember, is just a list of characters. So a list of characters is, we need to hash each element in that list one at a time, and then find some way to combine them together. Okay, and there are a couple clever ways we could do that. One, we could just add them all together, and that might work. That would be interesting, but that causes a lot of chaos down on the lower end bits. Okay, not so much on the upper end bits. And then we could, there are other things we could do, but we could maybe multiply them together. We could just concatenate them all together. That just makes a really big long number, so we don't want to do that. And in fact, actually, if we did just concatenate them all together, that is, take the 8 bits of one character, take the 8 bits of the next, and then treat that as an integer, what we're actually doing is we're treating the string as an integer in base 255, okay, which, or sorry, 256 actually, which means that all of our digits have values in this range, 0 up to 255. Those are the values of our ASCII values. And then the place values increase by 256 every time, or a factor of 256 every time. So our first place value is 1, the next is 256, the next is 256 squared, whatever that is. I think it's 65,536. The next one is that times 256, even more. I don't know what that one is. Okay, so this is a very large number. Okay, if you even have a string of, say, length 5, you've gone up to 256 to the power of potentially 5 almost. Okay, that's a very large number that we've got written down. The problem with that number is it gets really large really fast, and then if all we're going to do at the end is mod it by 12 or something small, all those upper end bits, we've ignored them. We don't use them for anything. There's no point. Okay, so instead of treating it as a base 256 number, what we do, and the next clever step, the next clever improvement, is to say, okay, well, some of us might have looked at those ASCII table and said, hey, a lot of those characters we don't even use and they're wasted. And most of the characters that we do use all occupy this one space in the table, which means a couple of their bits, higher order bits, are always the same. So those bits, we should really just ignore them. And here's the thing, we're not actually going to ignore them, but we're going to say, hey, what if instead of 256, we moved our base down to, I'm going to move down for a second to 32. okay, to base 32. What that would do, if at base 256, that's saying at each point shift our bits over by 8 bits and then place the next number, in this case the next character value. In base 32, what we're saying is shift all the bits over by 5 bits and then write the next one, which means those top 3 bits, we're ignoring them by just not shifting them over and letting them play as large a role. They are still going to add up and flip a few bits down below if they're ones, but we know that impact will always be the same every time we do this. So that's the next step. The next step we said is we can, basically what that does is it makes that number that gets really big really fast get really big not quite as fast. So we've shrunk down the size of our number a little bit by making it in base 32 instead of base 256. Now here I said this is a real sort of. We're not really treating it as a number in base 32 because this value, this SI, in base 32, the highest this could be would be 31. Well, some of these are 255. So we're fudging things around here, but this is engineering at work. Okay, we're just trying to make something that works. Okay, so what about the last step? I keep saying base 32, but here it looks like we're in base 31. So why are we in base 31? Well, base 31 is a very special number. 32 is a special number because it's a power of 2, and 31 is a special number because it's a power of 2 minus 1. And these two different kinds of numbers have very special properties. In a power of 2, think in binary for a second. In a power of 2 is going to be a 1, 0, 0, 0, 0, 0, some number of zeros. And what it means is being a power of 2 is if you divide it by 2, you always get another power of 2. So another 1 with 0, 0, 0, 0, 0, 0, zeros. Again, very convenient in a lot of computer science math. What about a power of 2 minus 1, like 31? Well, if you divide it by 2, okay, well, it's odd, right? Well, if you divide it by 2 and take the floor, you will always get another power of 2 minus 1. So just like the powers of 2. So it's got this other nice special property. Okay. The other thing is, so if our power of 2 is a 1 with a bunch of zeros after it, our power of 2 minus 1 is a whole bunch of 1s. And so our 31 here is a whole bunch of 1s. So by multiplying by this, what we're actually getting is a whole bunch of interference with the bits. 1 with a bunch of zeros is just a bit shift, but a whole bunch of 1s is a lot of interference, lots of bit flips. Okay, and that's going to be important for giving us a sort of a randomness in the hash value, and we really want randomness in the hash value. Okay. Okay, so that brings us to that last step. The actual last property of 31 that actually makes it even more advantageous is it's also a prime number. And so this is a power of 2 minus 1. That's also a prime number. This is a special kind of prime number. And so because of all these reasons, it's sort of 31 becomes this really special number for hashing strings. And it turns out that this hash is a really efficient hash at hashing strings in Java. For how do we judge the efficiency? How do we, measure how good this is a hash code? Is how uniformly it spreads the different strings over the different values that you can compute. Okay. Now here I say this number is still going to grow really big, really fast, but we return this value as an integer. Okay. And so that means we're going to do a mod 2 to the 32 on it. Okay. All right. So this is just an example of how Java has built in an overriding these memory addresses to make strings work as expected. And if you're hashing strings, then it means you don't have to worry about this if you use Java. If you're hashing strings in some other context, you might have to build your own hash function. And if you do, here's a good way to do it. Follow Java. Okay, so I mentioned earlier that some of us might already be anticipating some problems, and um, one problem occurs using the mod operator as we had, taking our keys in the range. Well, there's more than one key then that will be mapped to each index, each bucket. And if two keys are mapped to the same bucket, we call this a collision. And most of the time this is unavoidable. If it isn't unavoidable, if it is avoidable, I guess, then we call this perfect hashing. Okay, so perfect hashing will be a case where every key has exactly one bucket it belongs in, and often we don't rely on perfect hashing because that means we end up having a lot of buckets when there's a lot of empty buckets when there's a lot of buckets with no keys associated with them. So a trade-off of having memory space is that by shrinking the size of the array we're going to use that's closer in line to the number of keys we have, we end up having more potential for collisions. Okay, so I've got a quick example here. The two numbers 35 and 58, if we do our hash function here, mod 23, both of them give us 12s. So that means both of them would belong in bucket 12. So handling collisions depends on how you want to implement your hash table. There's more than one way we can do that. And actually there's sort of two primary methods. These aren't just a method in their own, they sort of have sub-methods beneath them. But the two main ideas behind how we can handle collision are one of two ways. Either, well, we just store all the entries that belong in that bucket. So that means that's chaining, our first one. Our buckets aren't just a single entry, they're a list of entries. That's one way to handle it, but say you don't have extra space available, or that's going to be more problematic than it's worth, then another way to do this is what's called probing. Now, probing is where we just find another location. So say you try and add a key into a location that's already occupied, while you just go find another space, often nearby, say the next door neighbor, and place the key there instead. And because there's lots of different ways you can look for another location, there are lots of variants of how you can do probing. And we'll look at a couple of them. In fact, I think what I want to do is I want to leave looking at these collision handling techniques to our next video. So, well, thanks for watching this video, and we'll see you in the next video.